We have a yacht leaving a harbor with position vector x, y in kilometers relative to the harbor at a time t. So this equation makes sense that there is no vector. I mean, you could have xy equals 0, 0 plus t 5, 8 if you like. And that 0, 0 would represent that it's right at the harbor to begin with. A cargo ship is not at the harbor to begin with. At that same time t, it's at 6, 3. 6 kilometers to the east and 3 kilometers to the north. And it's traveling in a different direction vector. So finding the speed of the yacht, well, this vector equation says when time is 1, it's going to travel 5 to the right and 8 up. So if we find the length of our direction vector, 25 plus 64, which is the square root of 89, that will be its speed in kilometers per hour, because that's how far it's going to travel in 1 hour. If you think about it, here is the harbor at 0, 0, and when t is 1, it's going to end up there at 5, 8. So that length is just a squared plus b squared equals c squared. That length of root 89 is how far it traveled in 1 hour. So if we're trying to find its speed, it makes sense that it's going to be root 89 kilometers per hour. Find the distance of the cargo ship from the harbor when the pleasure boat, I guess our yacht turned into a pleasure boat, starts its journey. Okay. Pleasure craft it should be. There we go. Pleasure craft. So when it starts at 0, its journey is at time equals 0, and at time equals 0, the cargo ship is at 6, 3. How far away is 6, 3 from the harbor? Well, again, if you think about where 6, 3 is, you want to find that distance. It'll be a square root of 45 kilometers away from the harbor. So 6 and a bit kilometers away from the harbor. If both the yacht and the cargo ship continued on the same course, and the people on the yacht, because it was a pleasure craft, weren't paying attention, would they collide? Cargo ship doesn't matter, it's just like a speed bump, right? But let's figure this out. The way that we can do this is we can look at our parametric equations for both of our graphs. Our first one, 0 plus 5t and 0 plus 8t. You wouldn't have to put those zeros in there, but this is your yacht. Or your pleasure craft, yes. And if you went for your cargo, your starting point is 6, 3 and 3, 7. So 6 plus 3t and 3 plus 7t. Did I get all those numbers right? Yes. Those are our two parametric equations for them. So there's only one variable here because time is time. Whereas some of the other ones, when we just tried to find them intersecting, we had two variables, a parameter of t and a parameter of s. Now time is time, so there's only one variable, and we can solve, if we equate the first ones, we have 5t equals 6 plus 3t, solving for this, we get t is equal to 3. What we have to figure out is that same thing happened with our y-coordinates. If we try to solve for our y-coordinates, 8t equals 3 plus 7t, does t equal 3 here as well? And if you solve this, sure enough, t is equal to 3. So the fact that both the yacht and the cargo ship are going to be at the exact same place in 3 hours means that they will collide. And if you wanted to find exactly where that would be, you could plug in 3. So at 3 hours, they are both at. So if I plug in 3 into either equation, I get 1524. So they will collide. And then it'll be a not so pleasurable craft. So here we have a nice long reading question. So the diagram shows a circle with a radius of 25 and the origin being the center. And we're imagining there's a lighthouse at that origin which can see out with that radius of 25 kilometers. There is a ship initially at P 31 kilometers to the west, so that would be about there, and 32 kilometers south of the lighthouse. And the ship is moving parallel to the vector 4, 3. So it's going over 4, up 3, over 4, up 3 at a speed of 20 kilometers per hour. An hour after leaving P, the ship is at a new point R. So can you imagine this direction? That is the direction that it's headed. And if it's going 20 kilometers an hour, it's going to end up at the point R. So first of all, let's write down our position vector, OP. Well, if it is 31 to the west and 32 south, that'll be our initial position vector for our ship. Show that the path of this ship can be given by this vector equation. Well, we want this as always our starting point. And this is our velocity vector. We already know that the starting point for our ship is at negative 31, negative 32. What we need to do is we need to find the velocity vector. And the number one mistake made by students in questions like this, where they want you to show something, is that the answer's right there, and you're so tempted to use it to show that it works. Right? That is the problem, because you're using your answer to show your answer, and it's sort of circular as far as the argument goes. So we need to show that our velocity vector is 1612, and we need to use the information that we're given, not the answer that we have, to show that. Does that make sense? So the information that we're given is we're given that it travels parallel to 4-3, that's its direction, with a speed of 20 kilometers an hour. If we look at 4-3, and we find the length of 4, 3, a squared plus b squared, we get that 4, 3 has a length of 5. In other words, if that was the velocity vector, then the length of your velocity vector is the speed that it's traveling. So currently, this one has a speed of 5. We need ours to have a speed of 20. So you could find a unit vector with a speed of 1 and then multiply it by 20, or can you see that in order to get a length of 20, you would need to multiply this one by 4, because its length right now is 5. So if we multiply by 4, we'll get a length of 20. And then that length of 20 will be a speed of 20. So if I take my vector 4, 3 and I multiply it by 4, I get 16, 12, and this is my velocity vector. And so now my equation of my line will be my starting point plus t times my velocity vector. So if we want to find out what the vector OR and what the vectors PR are, then it's like a pirate. Well, we know that we get to R 1 hour after. So we can take our equation of our line and say 1 hour after traveling with that velocity vector, we're going to get to the point R. So OR will equal negative 15, negative 20. And that would be the position vector of OR. If we want to find, so we've got our origin here. We had our point P. We have our point R. And we want to find the vector PR. Well, you could use your position vectors because you know your position vector for OP and you know your position vector for OR. You could say, how can I get from P to R? I could go back to O and then over to R. So that would be negative P plus R. And if we did this, we get 1612, which kind of makes sense because if you think about what happened, right, why is that exactly the same as what we had right here? Well, P to R is just traveling our velocity vector for 1 hour. You're going to go 16 this way and 12 up. So sort of two different ways you could look at this one. One, you could just use your vector equation and say, that's the direction that I'm heading. And if P to R is just doing that for 1 hour, I'm going to travel 16 and then 12. Or you can use what you know about position vectors and say, anytime I have my position vectors, I can find my equation of my new vector by going negative P plus R. And that works as well. show that when the ship reaches R, so remember that R was negative 1520, it first becomes visible. In other words, since the lighthouse has a radius of 25, in order for it to first become visible when it hits the point R, R needs to be 25 kilometers away from the origin. The way that we would figure that out is just to find our magnitude of R, 15 squared plus 20 squared. And sure enough, it's equal to 25. So we could write a little statement here. Since R is 25 kilometers from O, the ship becomes visible when it gets there. And you can't end your notes without a good collision. So, another ship. Notice that all of our questions so far have resulted in destructions of pleasure boats and running into poles. So, we have another ship. Will these boats collide? Does Mr. JR like boats to collide or not? Are the questions more exciting if they do? So again, we can look at our parametric equations. So our first one there's our equation from our first boat, and now our new boat, the parametric equations look like this. Again, we have two equations that we can equate. We only have one variable, so we can solve for t for time in both of them. If the times are different, then they're not going to collide. If the times are the same, they are going to collide. So with our x coordinates, if we make negative 31 plus 16t equal to negative 7 plus 10t, we'll get 6t is equal to 24. T is equal to 4. And if we look at our y coordinates, negative 32 plus 12t is equal to 4 plus 3t. Uh-oh. Where are they when they collide? So if you plug in 4, they are at 33, 16. Oh. I was imagining, if you were in the lighthouse, could you see it happen? No. So a little bit of disappointment in the end, because you imagine yourself in the lighthouse. But no, you will not be able to see them crash into each other. So. They're two separate equations. The green one is your path. So if you think about y equals mx plus b, okay, you've got your green boat happening this way. and you've got your blue boat maybe traveling like that. It's not exact, but just to give you an idea. Okay? So we've got to imagine, okay, here we go, make pretty boats. There's our boat on the green path, and, ooh, purple boats. There we go. So we got going this way, going this way, right? And according to their equations, it could have happened that they cross, right? But if they cross at different times, it's going to be fine, right? In fact, that happens all the time on lakes, right? There's boats that have traveled where other boats are, and it was like, that was yesterday and today's today. They don't crash. That's okay. But the problem happens is that at time equals 4, they happen to be at the same place at the same time. Well, it could be, like when you're saying, why do I have to do this one too? If I solve for this one, like if I change one little thing in this equation, I said, these guys happen to leave at 5 instead of 3. If I did that and I put in 5 instead of 3 and I move things over, I would get 37. And solving that, that would be 4.1 instead of 4. So that means that that boat isn't quite, it's not quite at the same place. It's a narrow miss, perhaps.
So how do you, because one of those paired with Y, like you have both of the formulas are put together.
And the reason that's important is we could be at the same x coordinate and different y coordinates, and we could wave at each other, but we wouldn't crash. But if we are exactly at the same x and same y coordinate, we would crash and high five and have a number of other body parts probably run into each other, but that wouldn't necessarily be a good thing. So if they're at the same place at the same time, that's going to be a collision, right? It's in respect to time. All have to be corresponding, right? Because you could have.
T is X, sort of, because we always think of T as X.
Yeah, the T here is time, and it's telling you where this is the pathway that this boat goes, and everything is good as long as something's like even this is fine, right?
Yeah.
But as long as they're not here at the same time.
Right, because you're figuring out when they're both equal. I get it. I get it now.
Go.
I can't even see the boats anymore. Whoa. Oh, no.
So sad.
Where's the other guy? Is he
Vaporized. Yeah. Yeah. It was very sad. Okay. I've already given this out to you.